Hi, everybody. My name is Riley. I'm the team lead for Clause, and I'm joined today by Emily Rassel, our software lead, and our UI UX lead, Cesar. So today we're going to be talking about how Clause is bringing innovative software technologies to human space exploration. Oops, sorry. So Clause stands for the Collaborative Lab for Advancing Work in Space, and our team is very multidisciplinary. So we have students ranging from undergrads to master's students in a variety of departments across the university, from LSA to engineering and School of Information. As you can see on the left, this is our team diagram. And while we're primarily focused on software development, we have a lot of other supporting teams as well, such as UI UX designers, our human in the loop testing coordinators, our outreach leads, and our hardware team as well. So these are just a few pictures from our meetings. So on the top left, that's one of our all hands meetings. On the top right is a workshop we gave to new members on server and networking. And then on the bottom left is from our trip to Johnson Space Center last year to test a prototype. And on the bottom right is a UI UX team meeting after we had to transition online due to COVID. So the motivation behind the starting of Clause is that currently EVA procedures contain technology such as cuff checklists and other things that are more on an analog basis. So what we wanted to do is bring technology, modern day technology, to these procedures. So in addition to replacing cuff checklists with some sort of digital and more modular and adjustable mission plan, we also want to help out with taking notes during planetary sampling and making these procedures more streamlined, as well as helping with lunar navigation. As we're moving towards Artemis, we want to make sure that we're efficient in our navigation of the moon, and as we become more autonomous, this will also help with that as well. So in addition to all of this, we want to also highlight pre-ops planning so that during and after a mission, we're able to see what we had originally planned for a mission versus how it changed depending on things that we found along the way. So the goal of Clause is to create human-centered, software-driven applications to further humanity's presence in space and streamline mission procedures. As you can see here, we have a few pictures using the Microsoft HoloLens. This is an augmented reality headset. And for those of you who aren't familiar with augmented reality, it's a superposition of digital content on top of the real world. So while these people are using these headsets, they're able to see digital information as well as their surroundings. So what are people doing in industry? Obviously, this student team is not the only people working on this kind of technology and incorporating it into space exploration. On the left, you can see the Joint Augmented Reality Visual Informatics System mockup. This is called Jarvis, and this is what a current NASA team is working on right now. So with this headset, an astronaut would be able to see information such as navigation, mission procedures, as well as biometric information. On the right, you can see that this is a field trek somewhere in some mountains or a volcanic region. And this is during a field trek where they're doing geological sampling. So in this case, the holosextant was a project to streamline this field trek procedure using Microsoft HoloLens technology. So brief history of Clause. Clause was started in October of 2018 when it submitted to the NASA Suits Challenge. This challenge was inspired by the current Jarvis project and getting student opinions on how they can innovate this interface. So we sent a proposal into that, and we were accepted in December of 2018. And then in April of 2019, we were able to test our prototype at NASA Johnson Space Center. So these are just a couple of photos from that trip. Out of this came Modernizing EVAs for ISS astronauts, or what we call MEISSA. And this is our interface that we created on the Microsoft HoloLens. This is actually a screenshot from using it that we then overlaid onto a background that fit the situation a little better. So in this case, you can see mission tasks on the top left, and then on the bottom right, you can see health information. You also see warnings in the top middle. So this is the start of our project, and from here we've gone on to do other projects as well. So this year we're continuing with the NASA Suits Challenge. This year, however, it's more focused on the Artemis program after its announcement. And so with this comes a lot of new challenges to overcome. So things such as surface navigation, rover repairs, and other aspects of a lunar mission that are unique from an ISS mission. In addition to this, we're also teaming up with Bliss to work on the NASA XHAB challenge. And for this, we've been working on an AR system for field treks. So this is more focused on the geological sampling procedures and surface navigation.
Hello, I'm Cesar, and I'll be taking you through our team's main project, Atlas, which is short for AR Toolkit for Lunar Astronauts and Scientists. This is our solution to improving the operational efficiency of astronauts and scientists with respect to all the things we mentioned on the last slide, including EVAs and field trips. So just like our team, Atlas isn't just focused on code, but is very multidisciplinary as well. Here's a high-level overview of our system, which is broken down into hardware and software components. On the hardware side, we have our mobile support equipment, or MSE for short. This includes basically everything that the astronaut will be carrying with them out into the field. The other side of our hardware is our server, which is currently locked away in the basement, but this runs our web server and database and is essential so that our HoloLens and our mission control center can actually talk to each other. As for the software side, includes, of course, all the code and infrastructure running on the HoloLens. It also includes a mission control sensor, which you'll see more details about later, and also includes a graphical user interface that was created by our wonderful team of designers. Here's a more in-depth look into our hardware components. Aside from the HoloLens, we have all these different sensors and electric components that will be held inside a backpack worn by the user. For example, you can see we have secondary cameras, a GPS, an altimeter, and all of these will be connected to a Raspberry Pi. This is all to provide HoloLens with even more information. Also in the backpack will be things to support all of our electronics, like power bank and external hard drive. And there'll also be static tools to help with geology, like sample containers with QR labels. Here is an overview of our software. This divides the software up into infrastructure on the HoloLens, as well as code on the mission control center. So for the HoloLens side, we broke down our components into different protocols and modules, which is just an abstraction of handling different situations that the astronaut will be in throughout various stages of a mission. As for the mission control center, this can be thought of as like a real life mission control room, plus some more capabilities that are relevant to our system. This serves as like a central hub where the astronauts and scientists can come together to plan future missions, monitor current missions, and also reflect on past missions. So under this umbrella includes a user interface, a database to store all the information that we generate, and the infrastructure to communicate with the HoloLens. So now we'll go through a few mock-up designs for our system. This first one represents the astronaut and what they'll see while on an EVA on the moon, and more specifically while fixing a lunar module. And this highlights just one way of presenting our mission procedures as well as our navigation. Here is another design that we have. This represents a slightly different situation, which is rock and sample collection. As you can see, this is another way of presenting the mission procedures. And on the right side, you can also see a minimalistic mission clock, as well as a view into the astronaut's biometrics. Here's a third mock-up showing the user interface for navigating between different modules. This navigation will primarily be done through voice because we can't really rely on hand gestures. And another component of our project is a conversational AI called VEGA, which stands for Voice Entity for Guiding Astronauts. This is just one of our ideas to improve astronaut autonomy while out in the field. And you can kind of think of this as one of the conversational AIs I use every day, like Siri or Alexa. And here's a look into what our current mission control center looks like. Again, this will be used by basically everyone on team in every stage of the mission. And so we thought it would be best to divide the MCC capabilities into 3 stages for pre, during, and post operations. So before the mission, for example, we'd be creating the tasks and procedures for the mission and plotting waypoints to show the astronaut where to go. And during the mission, the supporting team will enter the control room page, which will give an overview of everything that's happening with the astronaut. So here they can monitor the biometrics, modify procedures and waypoints, and also send and receive communications. And finally, after the mission, the team can all come together and go through the past mission and use this new knowledge to improve upon next mission, and the cycle starts over again. Here's a screenshot of the navigation page on the MCC with an example waypoint off the coast of Cameroon. Here you can go through different waypoints, see what missions they're from, and see the information related to that waypoint, such as field notes, rock samples, and photos. Here's a look at our field notes manager, where we can go through the astronaut's notes, take it from different locations and from different missions. And finally, here's a look at one of the simulation tools on the MCC. Here we can toggle warnings that have to do with different parts of the suit, like suit pressure warnings or cooling fan failures. This will be used later when we conduct human-in-loop testing to see how our system behaves when facing different problems.
Sorry. So hello, I'm Emily. I'm the class software lead. So although we're a newer project team, we still continue to recruit new talent and think about the future of the team. So I'm here to just share some ideas for how we can expand our current system's capabilities. So first we have RIGEL. So we would incorporate machine learning, specifically computer vision technologies, to help the astronaut identify rock hazards and potential geology samples. So the current technology doesn't exist to say exactly what the composition of the rock is, but we could at least help the astronaut identify sites of interest. There's also a lot of open source databases that we could use to train the model, and then we can always refine it as more images of rocky terrain and data comes back from the moon. So we showed this picture earlier, and this is RIGEL incorporated with our Atlas project. So in the center, you can see a black box identifying a potential rock that the astronaut could pick up with a descriptive tag and then a prompt to take a photo or interact with the sample. So next we have a distributed lunar network. So with this system architecture, we could support more than just one HoloLens or astronaut and over a wide range of space. So the technologies that this would include would be distributed computing, peer-to-peer networking, and also expand upon our hardware sub-team. And this is a newer idea, so the design isn't fully fleshed out, but it would incorporate something like a master node communicating with the mission control center, and then other like follower nodes that communicate with the nearby users. And then finally, we would incorporate machine learning into our biometrics protocol. So this would be used for modeling resource depletion on the fly or doing early warning detection. So for instance, if water was depleting at a rate that wasn't nominal and mission control didn't realize it, then they would be notified preemptively, and then they could also visualize the data so that we can find the issue sooner. So we just wanted to say thank you to all of our supporters. Dr. Leah Sterling is the class faculty advisor, and she's provided a lot of feedback throughout the year. Also, the NASA Suits team and NASA Survey through the XHAB Challenge have supported our project. Bliss and the class department has given us lab space and resources within the university. And then we've gotten funding from a variety of sources, including the Michigan Space Grant Consortium, the CSE department, and the Office of Student Affairs. So without all of their support, we wouldn't be able to do the project. You're good. And so thank you so much for listening. We love to engage with everyone. So we have a website and an email link. So feel free to reach out to us at any point and we'll be around for any questions.